Greetings, magnetic friends. We are going to start with some sources of the magnetic field and how to calculate it. This is going to start with our new stuff post the second celebration. So we're going to start with essentially a Coulomb type of way, I guess you'd call it, because it's a more of a mechanical way of calculating to integrate on the distributions that are causing the magnetic fields. And then, just as we did with electric fields, we're going to slide into a quicker way of doing it, which is via the fundamental law. So let's start first with drawing some analogies, which is kind of a funny thing to say because Coulomb's rule was actually discovered after what we're about to do now. So let's go ahead and get started and see what we come up with here. Let's start with the sources of the B field. So we know that magnetic fields are made by moving charges, and one of the ways that we can think about that is with an electric current. So let's imagine that we have a current distribution, and we would like to find the magnetic field from something like that. So, well, we've been talking about forces. So let's suppose we want to find the force on a electric current due to another electric current. All righty. So this is kind of how it goes. If you recall, from the E field section, when we went to look at Coulomb's rule, and we were thinking about the force on a charge from a charge distribution. So suppose we had a charge here. Suppose we had a charge here, and it was Q1. And let's suppose it's positive just for smiles and giggles. And over here, there's some charge distribution. We'll call that Q, capital Q2. And there's a small itty bitty piece of this thing here, which is dQ2. And that dQ2 makes an electric field. And the electric field is out here, and let's suppose this is also positive. I forgot to notate that, but let's suppose this is also positive. And therefore, the electric field made by dQ2 is going to be dE2, and it's going to be out here at the location of charge Q1. Let's suppose it's doing that. So at the location of charge Q1, the electric field looks like this. That gives rise to a force on charge Q1, okay, which is dF, say 2 on 1 here. I'm not sure if you can read my thing here. So let's make that 2 on 1. There we go. So that's the force from charge 2 on charge Q1, and it's the small itty bitty part that dQ2 is making on Q1. So what we would have done was we would have written for dF21. So if we want to calculate the force of 2 on 1, we would have said, well, via the Lorentz force law, right? We would have said that's Q1 times dE2. Okay. So it's the charge that's sitting, it's the charge Q1 that is sitting in the electric field dE2 made by charge dQ2. All right. So that's kind of where we were at. And then we said, okay, well, if we want to find DE2, we can integrate over Q2 and add up all the little pieces of Q2 in order to find the complete force, or in the way we did it, we found the complete electric field. That is E2 at the location of Q1. All right. And then you can multiply and find what the total force is. Okay. So now let's suppose we kind of going to keep that in mind. Okay. Keep that in mind. Now it is for B fields. We have two electrical currents. Okay. I'm going to have an electric current here. And let's suppose that I have a certain length of this wire. Okay. So a certain length of wire L, and we have a current running along it, and we'll call it current I1. Okay. And so there we go. On I1, there's a force because next to I1, okay, here's a current I2. All right. So now what we have is we're going to have a force on I1 due to I2. So we're going to take a small little piece of I2, which is, say, this piece right here. We'll call that a ds value here. And just as we did with, what was it? Just as we did with the force IL cross B, we put a vector nature on the L. So I'm going to put a vector nature on this ds, and I'm going to call that vector ds. Well, if I do that, I better try to draw it properly then, and not just say it's a distance. All right, so we'll say ds. We're going to say ds has the same vector nature as the current. So for ds, it's going to be that little piece right there. Okay. All right. So then that little ds piece of current is going to cause a force on I1. So suppose that we're looking at I1 here. Now, the problem here is that, I'm going to have, I can only draw a piece, the force on a piece of I1, but I'm going to use the entire I1. I mean, the entire length of I1L here. So I'm going to say, all right, well, suppose that right up here, I'm going to take the effect of the current on ds, and we're going to say, well, what's going on here with this? What's this piece of ds? What's the effect of ds on I1L? All right, so this will be an r, this distance here. Okay, well, all right, well, can you see it's vector pointed that way? Like that. Okay, so R is going to change its value. It's going to change its magnitude and direction as we take it from along different points of I1. Okay, along different points of L. So it's going to kind of go pointing a little bit, maybe about 11 o'clock, and then it's going to kind of go all the way out to maybe a little past 1 o'clock or something like that. It's going to go between there and there. Okay, so we're going to sweep it like that. Now, what we're going to find is that the force, okay, here, df of current 2 on current 1, all right, is just from the modified Lorentz rule. It was I1 L. Okay, so we give L the same vector nature as the current. So it's pointed from left to right. And that's going to be crossed with dB2. All right, so the force on current 1 is due to the field made by current 2. All right. And so what's happening here is if we make a little analogy, which it's not that bad of an analogy, but let's look at what we have between these two things, right? We've got dF21 for the electrical case. I've got dF21 for the magnetic case. So let's compare and say that Q1 is essentially, if I think of the fields as being the comparable things, okay, if I think of the fields as say, look, I've got a DE2 and I've got a DB2, all right. So if I take a look at Q1, then we're gonna say here then that Q1 or actually maybe, well, it's probably the other way around. So I is going to be the stuff in the front side. So it's going to be I1L crossed with something, which is kind of a funny way to write it. But it's I1L crossed something, and then DE2 and DB2, right, is we're going to look at the fields as being things that we can calculate via the same types of methods. Okay. So if I look at Q1 as being I1L crossed with something, and I'm realizing that the force on Q1 came from DQ2. So then what we're going to say then is that if I have a Q, then I'm going to replace it with an I1L cross the field. That means we could write DQ2 as equal to, well, or something like, I shouldn't say equal to, maybe this is a little bit, maybe I should say it's more analogous. It's not equal to, it's there. I'm only trying to draw an analogy here as to how to calculate the B field. So DQ2 then would be I'd have to change the subscript because now I'm talking about 2, which is the source of the field. And I'd say IDS crossed with something. All right. All right. So if I take how we calculated the electric field, all right, so from Coulomb's rule, now we're going to go one step further. And if none of this is making sense, don't worry, that's pretty normal. It is a little bit nebulous, and the point of all of this will become clear in just a minute. So from Coulomb's rule, I'm going to calculate the electric field DE2. Okay, so go back up to this original one, and I want to calculate DE2, right? That's what we did with Coulomb's rule, and that means that I could just say, all right, I know how to calculate that. It's the field of a point charge. So it's going to be K times DQ2 divided by R squared, and then I got to throw the vector part of that in, and that's called, and that's called R hat. So R hat, if you remember, just in case, it's the unit vector that points from that points in the direction of Q2 to Q1. In this case, DQ2 to Q1. And that kind of gave you because they're both positive charges, that going to give you the nature of the field, because it should be a radially away pointing field. Okay, so let's write the analogy. Since I have that now, so now I want to calculate dB2. How am I going to do that? Well, I'm going to look at what I did for Coulomb's rule, all right? And remembering that dE2 and dB2, I wanted to kind of consider those things, the field bits, right, that I'm going to try and calculate. So from Coulomb's rule, I had a constant, and so I can't have the same constant because this is a magnetism, so I'm going to call it K, but I'm going to put a little M underneath it for magnetism, and I cannot use B, because if I use K with a sub B, that's Boltzmann's constant. We can't use that. All right. So we're going to use M for magnetic. And now I'm going to look at this thing here. I'm going to say, okay, DQ2. I've got an analogical, and I've got another way to write DQ2. Okay, I'm looking at that thing right there. So if I just take that for DQ2 and substitute that in, I'm going to get an I to ds vector crossed with something. I'm going to divide this thing by r squared, and I'm going to have to multiply by r hat. So that's what the thing's getting crossed into, is the r hat vector. Okay, so essentially the same deal here. The unit vector r hat is pointing from the ds section of I2, right? It's just what I've labeled here, towards I1. That's the entire vector r, so the unit vector r hat is just pointed along that direction. Okay, so by analogy, what we would have done to Coulomb's rule is we would have integrated up both sides, and sure enough, right there and right there, and that's an integral over the Q2 charge distribution. Now, by analogy, I have this thing here, which is a monster. It has all sorts of gross looking mathematical operations in it, all at the same time, which is nobody's friend. We're going to integrate this over ds, which is the second current. Okay, I2 ds, that's what we're integrating on. And all that weirdo directionality stuff with the magnetic field is wrapped up in the cross product. Okay, and since I know you love cross products, we're going to take a look at this. So what is this thing? Oh, it looks horrendous. And it looks horrendous because it's not that it is horrendous, but to do this, you can't look at the entire thing. I remember trying to learn this, and you can't. I just eventually, look, you have to break it up into bits. All right, don't try to tackle the whole thing all at once. This is known as the Biot-Savart law, but again, it's just kind of a rule. Okay, so that's what this is. It's the law of Biot and Savart. And they were French, well, they were French. I was about to say, oh yes, they were French physicists who did such great work, but actually I know absolutely nothing about Savart. Biot is a fairly well-known French physicist, but I don't know anything about the other guy. So who cares whose law it is? But anyways, so this is how people suggested we calculate the magnetic field of a current. And so to calculate that due to I2, this is how you do it. Okay, so this is a process. It really is. All right, so the only thing to do here is to do an example, because this thing is such a crazy looking thing. That if you want to know how to do anything with it, we have to break it down step by step. And so the example I'm going to do is essentially exactly what we just is the situation that we eventually just did. I mean, the one that we just did. So let's take a look at a current. that's traveling like so. And we'll call this, just call that, it's lying along the x-axis. All right. So here's a piece of current carrying loop, and it's got some distance here, here, s. All right. So I'm going to take a little piece of ds. Let's suppose once again the current's going to be running left to right here. So there's I2. And here's our ds. All right. So we've got our I2 ds. Now I'm up, suppose that we're up here, and it's, I want to make sure that I'm kind of off center here, so this doesn't look like it's a, yeah, I think that's off center. All right. So I'm up here and I'm looking at what is the magnetic field at my location due to I2. Okay. So this is like our point P. And we're asking find B here due to I2. And at this point, I need not really label it I2. It's just I, because I don't have another current here. It's right. We're doing the same type of process as we did with Coulomb. Initially, what we started off thinking about were the forces between charges. And then we said, oh, what if that second charge, or actually I call it Q1. So what if that first Q1 charge is not really there? Then you just kind of lose Q1 out of the way and you say, but there's still an electric field there. So the same type of process, right? What we just did was we went through and looked at the force felt between two current carrying wires. And now I'm taking one of those currents away and saying, what would be the magnetic field at that location? Even if that wire weren't there. All right. So what I'm going to try and do here is say, okay, here are my limits. So it's going to look kind of like this. One to there, and then one to there. See, it looks too midpointish, but all right. I'm trying to make this off the middle of the wire so that there's no, so that there's generality here. So the point being here that I am actually right here in between those two right now. Okay, so let me just label these things in here. Okay. All righty. So what we're going to do is we're going to look at, oh, and I should label that R like that. And so our hat is pointed that way along the red R vector. Okay. Okay. So there's the picture. And I'm going to say that this distance here is A. And then this distance back here to, let's just call this X, to where my point is right there. All right. Okay, so now let's look at how to use this I ds cross R over R squared integral thingy-majigger here. All right, so here are some problem solving steps. Okay, number one, you must draw this picture not this picture, but the picture of the field and the current and all that stuff that you're trying to calculate, and from where to where, and where's R, and what's DS, and which way is I2, and where's the point P. You got to draw all that stuff out. Because if you don't, I have no idea how. I mean, maybe eventually it's kind of like kinematics, right? Or force diagrams or something. Maybe eventually you don't need to do this, or you know the kinematic equation, so you write them down, or you just. I still need the picture. Okay, so what have I got here? I got ds cross r, and there's da 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 da. All right, so draw the situation, draw the picture of whatever it is that you are trying to calculate, due to what, at what point, with r and ds. You just honestly, I think that it's going to make a lot of difference if you do that. Okay, so then the next thing is going to be in the picture. All right, we're going to pick out where the ds vector is. We're going to find where r is. We have all of this stuff figured out. So we're going to write down. Okay, we're going to write down an expression for ds, and we need to evaluate this cross product. Because, like I said, take it one step at a time, and don't think about trying to integrate with the cross product in there, right? It's kind of like Gauss's law. The whole point of having the flux on the left side was so we didn't have to integrate that. Well, we are going to integrate in this case, but make sure you've got the cross product out of there first. Deal with the cross product. It's just a direction. That's all it is. The entire function of the cross product is to tell you which direction the magnetic field at point P is. Okay. You can evaluate the cross product. You can do it with math, and I would suggest use a right-hand rule, which is, I guess, going to be our right-hand rule number 2. You can do it with math if you want, like set up the IJK determinant and go for it. And we might do an example with that. I don't really, well, we'll see. I'm not sure how I feel about that yet. All right. The third thing here. So once you've written out what ds is, like in my case here, it's going to be dx. All right. So I'm going to have a dx cross r hat. And I'm going to have an I2, which is a constant current. I figured out what my r is, and I'm going to have to set up my limits of integration. So I need to, as you can see, I don't really want to, well, I can integrate dx, I guess, along s. But with the cross product in there, it might be more useful to think about a theta integral here. So check this out. Once you evaluate the cross product, if necessary, parameterize the integral. Okay. I'm looking at it and parameterize. I'm looking at it and I'm saying, well, yeah, I am going to have a dx, but that dx is going to be crossed into r hat. And whenever you have a dx cross r hat, there's kind of weird stuff that happens, like a sine is involved, a sine of an angle. And so if I have stuff like that, it might make it easier to integrate via the angle. So think about maybe a parameterization of the integral is a useful thing. If it's not, then don't do it. But if it is, then do it. Parameterize the integral and integrate on the wire. So you might initially look at this and say, well, this could be just a dx from 0 to s or something like that. But we'll have to see, because I got that cross product to deal with, and that mucks up everything. All right. So we've got that. So here, back to this now, what I'm going to do is I'm going to say, all right, so drawing the picture, check. So here's my ds. in this case, it's going to be dx I hat, all right, or dx x hat, whatever you like. So what does this mean? Well, if I think about the y direction would be up. I haven't labeled it on here because I don't have very much room. But if I did that, then the z direction is coming out at me. So that my coordinate axes essentially are going to look like your normal coming out at you, or if you like, maybe that's a little bit more, that's a little bit better of a description here. All right, so let's get rid of that. Okay. In fact, I'll just get rid of that whole thing right there and just say z is there. Okay. So this is your right-hand coordinate system, right? You take x, curl with y, and thumb point z. That's your right-handed coordinate system. So ds is dx I hat, and I'm going to cross that into r hat. So fingers with ds, or I guess with dx, and cross them into fingers with, I guess I really should say fingers with I hat, and then cross them into R hat. So let's set this. Let me do a couple of steps down here, and we'll come back to the picture. So dB at point P is K, the magnetic constant, which we got to deal with that, but I'll tell you what that is in a sec. Do you mind if I just call it I instead of I2, because this is a general procedure, but I called it I2, so I'll call it I2. dx, okay, divided by r squared. And then there's this I hat cross r hat. Okay, so now we're going to deal with that. I hat cross r hat. What is that? Well, back up to the picture. I hat, so put your fingers in the direction of I, which would be, it's just going to be that way. Okay, and now I need to curl them in the direction of r hat. So what direction is r hat? R hat's kind of, I'm going to have to lay my hand that way to go with the wire, and I'm going to curl them up like that, so that, because the direction of r hat is really this way, it's in the plane, right? So think about doing something like, nope, not that. Oh, well, actually, yes, that. Oh, why did I erase that? Let's do this. A, B. So you do A cross B. You'd put your fingers with A and you'd curl it towards B, but B is just right there. And then your thumb would point A cross B, which is going to be out of the page at you. All right. So the same thing's happening here. My DS, which has become DX, I hat. So I'm going with I hat like that, and I'm curling up with R hat, and thumb is pointing out no matter what you do. Now remember, these quantities, you're doing this at the wire, right? You're doing this. Here's your dx at the wire, your ds crossing with r hat at the wire. But the result of the cross product is actually located up here at point P. It's not down here with the wire. It's the direction of the magnetic field up at point P. All right. So if I go back to my A cross B, it's going to be pointing out of the page like so. Use the right-hand rule. I hat cross R hat, thumb pointed for you. See, it's weird. I know this, but just do it. It's pointed at you, right? Just like it's pointed at me. So that's going to be the Z. That's going to be the Z direction for me, right? Because if I look at X, Y, and Z here, my Z is the one that's pointed out of the page. So this thing is going to become K magnetic integrated I2 dx over r squared times the result of the cross product, which is a sine, because these two things, I hat cross r hat, they're not at right angles to each other, right? They're not at right angles. So I've got to have a sign in there, and I'm going to have a z hat. So that's the result of my cross product involving I hat cross R hat. They're not at right angles. Well, until you get to the point where they are, but that's the only point that they are. Okay. All right. So what we can do here is look at um, I guess what I'm going to say here is I want to think about that direction. So the direction is coming out of the page up here at point P. All right. Remember that I hat is on the wire and R hat's kind of from the wire to point P, but you're doing this cross product in order to find the direction of the magnetic field at point P. And that's the right-hand rule to let you know. Okay, so we've got this thing. What are we going to do with this thing? All right, so we have an r squared. Let's take a look back up here at what r squared is. So r is the hypotenuse of this triangle that I've marked with the x and the a here. So it's the square root of those things summed and squared and summed, and it's a square. So what we'll do then is we'll say, all right, where r squared should be equal to x squared plus a squared, like that. And the sine of theta, is going to be a over r. If you look back at the picture, my angle theta there, and so I'm picking out the opposite. All right, so that's going to be a over r. Okay. All right, so then lo and behold, if I transform a bunch of this stuff, I have the magnetic constant here. We will get back to that, don't worry. What do I have? So I have I2, I have dx, I have 1 over r squared and a sine of theta, which is a over r. So I'm going to have an a on the top with the I2 and the dx. So I'm going to have I2 a dx and a z hat. That whole shebang looks to me like it's divided by this thing to the 3/2. You can parameterize your integral. Okay. So this looks kind of like the integral of the line charge. If you remember back to the Coulomb method of finding the electric field of a line charge, this is kind of what it is. So the other way to go about doing this would be to form up the thing into a theta integration. Right? So I've got all of the sine theta, a over r, and all of this kind of stuff here. So since I've already got all that, then I can just go right off of this thing here, where a is equal to r sine theta. Okay. And kind of resub it back in, or leave the sign in there, or whatever you might like to think of. Then if I look at this, if I look at this thing here, the x side, if I look at the x side, this is a little bit funny, but I could write the x side as normally I could write x as being r cos theta. Or I could write it as A tangent theta. Is that right? Let's see. Let me think here. The tangent would be opposite over adjacent, A divided by X. Oh, no, it's not. So it would be X. If I put X here, that would be A divided by the tangent of theta. And notice that it's backwards. So the y axis is right there. This is the 0. So really this is a negative number, right, as I have it now. And so that's equal to the negative A, and then there's a cotangent of theta. Okay. So if X is the negative of A cotangent theta, then dx dx is going to be, let's see, if you do the d of cosecant squared theta, d theta, if I remember the trig identities right. Okay. All right, so if I do go up here, if we do this, then this thing's gonna turn into this awful mess again. Okay, and the I2 is constant, so we'll just pull that out of here. That doesn't have any part in the integral here. So now I'm going to integrate r sine theta for a. Well, wait a minute. Why would I do that? No, let's not do that. A is just a constant. Why would I do that? Let's forget that. A is a constant. Pull that out of here. Ah, no, don't do that. Dx, though, is a cosecant squared theta d theta. Oh, what else is constant? My z hat. I want that out of there too. Can I fit that in right here? Z hat. All right, that's going to be divided by this entire mess here, which is x squared. So I've got a squared cotangent squared theta plus a squared. That's to the 3/2. This is all in just simply trying to do the integral. So that gives me ki to a z hat. I'm going to want to factor an a out of this last one here. So I'm going to take an a squared here. So this piece here is going to become a squared 1 plus cotangent squared theta. Oh, that's good. And this whole thing is underneath the 3/2. So that means if I take an a squared out of there, it becomes an a to the 3rd, which cancels with one of these on the top, which makes it an a squared again. But I've already got an a sitting here, so that makes it really a 1 over a. All right, so let's cancel. This is going to be divided by, let's just go ahead and take the squared out and the cubed out, and there we go. So that's gone and that's gone. Okay, now I'm going to integrate the cosecant squared theta on the top. I have 1 plus cotangent squared theta here on the bottom to the 3/2, and that's d theta integrated. And lo and behold, that becomes cosecant theta squared, but it's under 3/2, so it becomes cubed, which just leaves me with all of this junk out the front. And it's now just the integral of the cosecant theta d theta, but that's just the same as integrating, isn't that integrating 1 over the sine cosecant? Oops, I got that wrong, didn't I? I did. This is 1 over the cosecant because it's cubed on the bottom. Now that's just integrating the sine. Ah, that's even better. Integral sine theta. Okay, so we're going to do the integral of sine of theta, and that is going from theta 1 to theta 2. Which I marked here in the picture, blue theta 1 and blue theta 2. It's really easy to just say, oh, look, theta 2 is in there. No, 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 it's not. You have to keep the same reference angle. All right. You have to keep the same reference angle. So if you're referencing your angle as off the x-axis, you have to stay as the angle goes, even if it comes oblique, or oblique or obtuse, whatever it's called, the big one above 90 degrees. So you still have to reference the x-axis as the 0 for the angle there. All right, so you're going to do this, and you're going to find that all of this junk here was done just so I set this up, and we were kind of, this is it right here. So this is your physics integral. Okay, all the rest of this stuff is math, just to try and figure out how to integrate this thing. And now that I've done that, the integral of sine is just the cosine, or is it the negative cosine? I think it's the negative cosine. So this is going to become negative I to z hat over a. And I'm going to do the cosine of theta 2 minus the cosine of theta 1. But the cosine of theta 2 is a negative number, right? Cosine of theta 2, look at the cosine. The cosine of this thing, it's more than 90 degrees. So that's going to be a negative number minus the cosine of theta 1, which is obviously a positive number. Okay, so that's good that I have that minus sign in there, because if I have a minus sign in here, it flips my direction. But I'm pretty sure that the direction is not flipped. It should be coming out of the page. So we just change this into a positive number, right? This thing here is less than 0. So ultimately B at point P is therefore equal to, the minus goes through, K magnetic I2 divided by A. There's a z hat, and then it's the difference of these two cosines. Yeah, you just got to love it when all of that gross mathematical junk just becomes, it's the integral of sine. It's like, oh, yes. Wonderful. You went through all the pain of doing the substitution. I also don't have to have some pain doing the integral, all right? So just make it something nice. Okay. So that's that. And the only last thing I have left here is to tell you about the magnetic constant, Km. Well, K from the, what was it? From Coulomb's rule, that's what I'm trying to get to. Km, so it used to be this thing, right? Well, hold on, hold your horses here. Get rid of that. So the K constant from Coulomb's rule was 1 over 4 pi epsilon naught, right? Well, something interesting happens here with magnetism. So the magnetic constant Km is really just that. It's really just K, but it's divided by C squared. where c squared is light speed squared. Or let's do this. So K magnetic here really is 1 over 4 pi epsilon naught c squared. And this is the way in which I will write it. Okay. I personally am all chock full of constants, so I don't need another constant, but you can have another constant if you like. And the textbooks, if you read about this in a textbook or you follow someone else's, they'll be referring to another constant, which I haven't introduced here. But that constant is also called mu naught. So the mu naught, so the 4 pi is the 4 pi. It's there. The mu naught has to be related with the epsilon naught c squared. I don't really, it, if you really want to call that another constant, that's great. I'm not going to do that, but you're welcome to. I like writing epsilon naught c squared, and that's just the way I do it. Okay, so suppose that we had, one of the steps I didn't write was to sanity check and do your. Notice I didn't say guess the answer, because right at this point it's a little too difficult to guess the answer. But number 4 is, I guess step 4 here is kind of important, which is do that sanity checking, do your limit taking, do stuff like that. Right at this point, there isn't much sanity in this. So it will become so eventually. But for right now, one of the limits we can do is to take this chunk of finite wire and make it an infinite wire, so that we can look at what happens when the ends of the wire get stretched to plus and minus infinity. What happens to the magnetic field at point P? Well, you got to come down here and look at what happens to the angles, right? So I had a difference in cosines of angles. So what's going to happen to theta 1 and theta 2 as theta 1? So as one side goes to minus infinity and the other side goes to positive infinity. So theta 1, I think you can imagine that both of these things, as the wire stretches to become infinitely long, both these things they're going to become basically flat. And the blue line is going to become on top of the black wire line in the drawing. So theta 1 is going to go to 0. It's just going to become, it's going to become so far away out there that theta 1 is basically going to be 0. And then it's going to be so far away that way, theta 2 is going to become 180. So we could do a quick, I guess that means I should write formally the whole full thing here, which is I2 divided by 4 pi epsilon naught c squared a z hat cos theta 1 minus cos theta 2. All right, so there's the answer with all the full constants and all that stuff in there. Now let's take the limit as s becomes infinity. All right, the wire length becomes an infinitely long wire. All right, so that means theta 1 becomes 0 degrees, theta 2 becomes 180 degrees. And that means that the cosine of 0 is 1, and cosine of 180 is -1, so it's 1 minus -1 in the difference of the cosines there. So then B, I'm not ready yet. There we go. So then B at point P is going to become it's going to become I2 divided by all of this stuff is still the same. Z hat, and then it just becomes 1 minus -1, which is 2. So it just sticks a 2 there. Yep. There you go. All that for that. Okay. So that's how you use the rule of biot and savart, or the law, if you like. So let's do one more. Let's do one more here, and then I'm gonna take a break, and then we'll do one more example after that in order to really get you cooked up thinking about the cross product here. So let me do one more, which is a little bit easier. Okay, another example here. Single loop. Okay, so here's a single loop of wire, and it's carrying a current I in it, which is, I like counterclockwise, so it's going to be going that way, like so. And I would like to find the magnetic field right here at the very middle. Here's my point P. All right, so try and see if I can't find the magnetic field at the very center of the circle. All right, so what I'm going to do is I'm going to say, all right, here, one there, and take a little pizza slice of this thing, and there's my DS. Of course, this is a very thin pizza slice that I'm taking here. So at that level, DS, that still looks like it has a turn in it. No, I don't want DS to have a turn in it. This is a straight. Oh, this is straight. Right? Because what I'm doing is I'm going to take such a thin slice that by the time I look at that little tiny chunk of the circle, it's just a straight piece of circle. So the angle here, I'll call that, I don't know, I'll call that d phi. Okay, and the radius of the circle, A. Okay. All right, so we're going to take a look at this, and we're going to say, all right, let's find what the magnetic field is in the middle of the loop. So let's just slam it with the biot savart, and that means that dB at point P is equal to I. It's equal to K over C squared I. Well, I should put that up in the thing here, right? I ds cross r hat divided by r squared. Okay, so ds cross r hat, there's my ds, it's tangential. the r hat vector is the one that points from ds to where I want the field. So it's like it's inwards pointing, right? So r hat, you got to be careful with this because it's always pointed from ds to where you want the location of the field, right? Your point P. So this one is actually pointed. Huh, that's weird. It won't let me overwrite the red color. Okay, well, fine. I'm just going to put it right here then. That is r hat. Okay, but note that ds cross r hat, it's a 90-degree angle in this case. So all our worries and fears are allayed because ds is tangent and r is a negative radial vector, right? It's right. ds is tangent and r is radial. So there you go. They're always at 90-degree angle, and therefore the field is again coming out of the page towards you. And r squared is just the radius of the circle, and it's constant, which is awesome. So this thing here, I'm just going to write this out. I'm going to say, well, ki over c squared, and I'm going to do ds cross r hat, but that's disappearing because my sine of theta is always 90 degrees. That angle doesn't change. The direction is out of the page at me, so that's in the positive z hat direction again. And I've got essentially left over a ds over r squared z hat, right? So ds is just going to go around the circle. I could parameterize that and call it an angular integral if you like, and do a 2 pi all the way around the circle, but ds is just going to be the circumference, right? So what I'm going to get here is put this up. Now we're going to integrate both sides, and I'm going to get the magnetic field at point P is going to be equal to ki. This thing here is just a squared, so that comes out. Ki over ac squared z hat. That doesn't have anything to do with the integral, so just bring the direction out. You're integrating ds. But the integral of ds is just the circumference. So that's just 2 pi times a. Oh, I forgot a squared in there, didn't I? A squared c squared. Okay, good. And then this is going to be times 2 pi a. Oh, well, now it's back to just being a again. If I could just go up a little bit, just go, whoa, not that much. So then I'm going to get I, and there's a 2 pi up top, and I'm going to have an 4 pi epsilon naught c squared on the bottom times a, and I already canceled that a, and there's a z hat, and that 2 pi can go away with this pi and that thing, which becomes a 2. So eventually what we've got here, what do we have here? It's 2 epsilon naught. Is that. Okay. So there's that. So that's the field created at the center of the circle. Notice that if we were not at the center of the circle, this would turn into a slightly more challenging problem. All right. So we've done a finite wire, extended it to an infinite wire, and now we've done the current loop. Okay, so that's how we're going to get started on the law of biot and savart, or really the rule, if you like. And I'm going to do, I think in the next one, I'll do one more. Oh, sorry. I'll do one more example, and then we will move on to uh, another electromagnetic law. And I believe that's going to be law number uh, 4. Yeah, it's going to be law 4. We've talked about law 1, which was Gauss's law. We've talked about law 3, which was the fact that the magnetic fields don't diverge and they always curl back in on themselves. So that's law 3. That's like the Gauss's law of magnetism, because everybody knows Gauss's law, and this is kind of the same thing except for magnets. So that's what we call it. And then we went on to number 4. We're going to talk about the effect of currents and on making magnetic fields, which is called Ampere's law. So that's going to be in the next one. All right. Happy day, folks.